well? Okay, thanks. I'm Guilherme. I'll just start with a little bit about myself, as everyone did so far. I studied in São Carlos at the USP in São Carlos. There, I did all my studies from the bachelor to the PhD. I'm an electrical engineer, so I'm a bit different from everybody here, probably. During my PhD, what I really liked to study was spreading processes on networks. And by networks, I mean simple graphs or multi-layer networks. Today, I would argue that they're basically the same thing. The idea that I really liked about this kind of models is that what we do is to create a really big stochastic process. We associate a lot of Poisson processes that are independent, and then they evolve on top of this network. And I always liked this idea that you can have very simple mathematical objects, in this case, the Poisson processes. We associate a graph that has some structure on top of that. And then we associate Bernoulli random variables, and then we put all of those elements together, and we have very complex behavior. This was actually my personal motivation to study these epidemic models. And of course, I must also say that it's also a nice problem because I think I don't have to argue too much that understanding how diseases spread in a population can be important. In the past, it was, the first slide would be, how important is this? Now it's easy, and I don't need to spend too much time on that. So with this motivation, I finished my PhD. I moved to Italy to continue studying this. I worked a lot with Professor Yamir Moreno, following more or less these lines, trying to make models more complicated, trying to understand different sources of heterogeneity, understanding, the phase transitions, how these models change, and then eventually I found higher order systems, higher order models. The first model that I found was simplicial complexes, and then I found this new object that I liked, that was the hypergraphs. So the idea was, okay, I've been working with complex networks my whole life, and at some point I realized that the graph is great, but in many real problems, the graph is actually a simplification. The system itself is a little bit more, I wouldn't say more complex, but it's different. It accounts for higher order kind of interactions. So this is what motivated me to shift my research toward these higher order models, but I kept the same motivation as before, both the personal and the application side for the Contagion. So this is basically my personal introduction, a little bit of already the academic motivation. And what I would like to do before I start my presentation is to clarify what I mean by contagion and what I understand by this higher order. So in this, for the sake of this presentation, the contagion can be disease, like COVID, for example, or any other disease that spreads in a given population, or it can also be some sort of social contagion. And social contagion here, I would like to ask you to interpret this as a very broad concept. It can be the spread of norms, the spread of ideas, the spread of behavior. Oops. And for a higher order, what I mean is an interaction that involves more than just one element. So just to give a few quick examples, we can be talking about this conference, because I am speaking to everybody at the same time. So the message, my message, is flowing from one person to many at the same time. And this is very, very different from the graph, in which I would have one connection to each of you And then my way of expressing, or my way of passing this message would be very, very different. So this is what I mean by higher order, and mathematically this will be modeled by a hypergraph. So let's start with some motivation. So my first motivation is this book, The Tipping Point, by Malcolm Gladwell, where he presents a lot of examples of what he calls tipping points. So for him, tipping points are, you see a system, a social system, it seems to be stable in a very simple state, for example, fashion. Nobody is using, I don't know, black tennis, or I don't know, blue shirts. And then eventually, from one day to the other, you see everybody's using. And then you think, well, it's because this celebrity was using that, and then everybody is using. And the fact is that this is not exactly what's happening. What is happening, and what Malcolm argues, is that there is a phenomena that basically, at some point, it's increasing, and then it tips. And for us, this can be understood as a discontinuity on this kind of behavior. So for him, he gives a lot of examples. Some of them I already mentioned: fashion. Another example would be crime. He mentions even diseases. And here I have to mention that his definition is not so precise, because it's not really a discontinuity. It's actually a continuous transition in that case. But this is a nice source of an informal motivation. The next motivation that I would like to point, and this is this is scientifically sound, is the evidence of tipping points in social conventions. This work was published in Science, and what they did there was they invited a lot of people in the lab, and they tried to see how norms change as we evolve. It's like an iterative game, and then we see how people change their idea to see if they converge to some new norm. And then basically they have a committed minority that is able to tip this behavior. So they actually verified that this critical transition, this critical mass, is around 20 and 30%. And this is very interesting because it's interesting, but kind of expected. This is in alignment with many sociological and political sciences studies, even etymological studies as well. And this is not really a huge surprise. If you talk to sociologists, they will probably agree with that. Is that correct? Yes. However, there are some other studies and some models that predict an even lower kind of threshold, even going to numbers like 1%, 3%. Examples of such lower critical mass thresholds would be languages, like English from the UK and the English from the Americans. They have a really low critical mass. They behave like a critical mass with a very low threshold. Okay, this is all very nice, but now I would like to make some turn and make the models more mathematical. So for us, the critical mass will be modeled as a half-side function. So I will have a threshold, and what I will do is to study how a population that is structured as a hypergraph will behave considering this kind of half-side function. So here, what I'm trying to say is that my assumption is that, assuming that this work is correct, that these assumptions are okay, so how can we go further? But before doing that, I would like to mention that this motivation is not the only one. This kind of critical mass is used in many, many contexts. And as Professor Gray mentions in her paper, it's a term that has been used by politicians, in newspapers, in many, for the public, and in scientific fields as well. Actually, this paper here is about the role of women in the Parliament of New Zealand, where she uses the concept of critical mass to model how these women in the Congress passed laws that are pro-women, like reducing the gender gap and this kind of things. And the critical mass is also there. So this concept is not only in this book, like, it's not only informal as the examples I gave, it's not only on this kind of laboratory examples, but it's also very well spread in many contexts, especially in sociology and political sciences. Okay, so I hope I convinced you that these kind of models are interesting. And the question that I could try to answer is, okay, if those models are correct, so how a collection of those models will behave? So basically, let's couple them together. We know that society is actually very well interconnected. So let's extend the concept of interconnections to higher order interconnections. So what kind of new behaviors we will see if we do this? We extend these models to a large scale model. So in this case, how the intersections between groups will change the whole dynamics. This is the real question that we have to answer. This is the real new ingredients that we are adding to the standard models. And finally, how can smaller groups trigger large-scale changes? Because we saw that this is 20% for one single group. But can we have a committed minority that will have a global change in a global scale that's lower than that? Can we see the whole system having a lower tipping point? This is the question that I want to understand. So, okay, let's start with the theoretical part. Let's start with defining the model itself. So, but before starting that, I have to define the basic mathematical objects that I'm going to use. So basically, our population will be modeled as a hypergraph. A hypergraph is a set of nodes and a set of hyperedges, where hyperedges are subsets of nodes, and they have no constraint about size. The hypergraph is as simple as that. For the sake of a comparison, let's put a graph here. A graph is the same, a similar object where we have a set of nodes and a set of edges, but the edges are constrained to only pairwise interactions, so only cardinality 2. In fact, every graph can be understood as a hypergraph. We are just imposing a new constraint. Okay, so since we defined our main object, let's now define the dynamical part of our process. So let's first define the dynamics inside one hyperedge. So what we do in the model is to associate a Bernoulli random variable for each node that we have in our hypergraph. This Bernoulli random variable will be 1 if the node is active and 0 otherwise. We are going to associate a critical mass dynamics on each hyperedge in our hypergraph that is given by this, that is defined by this variable tj, which is basically the sum of active nodes inside the hyperedge. And we are going to say that this hyperedge is active if it reaches a threshold that is that is defined before. So basically, we count how many active nodes we have, and then if it's larger than a given number, an arbitrary and previously given number, we say that this process is active. This is as simple as that. So we are interested in describing this model mathematically, and the probability that this hyperedge is active will be given by this Poisson binomial distribution, where we basically calculate all possible microconfigurations, which is kind of express this in this table here, and then we are multiplying all the probabilities of each micro-configuration here. And then we end up with an equation that is like this. This is very simple. There is nothing crazy about this, but here we find our first problem, a practical problem, not a theoretical problem, that multiplying small probabilities for really large hyperedges, it will be a computational problem because we are multiplying very small numbers, probabilities that are between 0 and 1, and then this is not numerically stable in practice on the computer. So this is literature, but it's nice. We can solve this equation here by using the discrete Fourier transform, and then we have a new expression for the probability that the hyperedge is active. This is not really a result, but it's just a practical way of doing things. So fine, we have defined our equation that describes the dynamics in one single hyperedge. So now we have to describe the dynamics in the whole hypergraph. The dynamics is described as follows. So first, we associate a Bernoulli random variable for each node in our process. It will be 1 if the node is active, 0 if it's inactive. We create a set of independent Poisson processes. We associate Poisson processes with parameter delta for each active node. So we are creating a sort of an SIS model. And this is the idea here. It creates an extension of the SIS model to a hypergraph, to a higher order system. Just a small parenthesis here. Why the SIS? Well, what we really want to do is to generalize the simplest model. So in the future, with the results we find, maybe we can refine this model and have more accurate models for predictions. But now our main goal is understanding. So going back to the model, we associate one Poisson process for each node with parameter delta, for each node that is active with parameter delta. This will model the deactivation process. Then for each hyperedge, for each hypergraph in our hypergraph, we are going to associate a critical mass dynamics as presented in the previous slide. So we have a defined theta j that will be given before we started everything, and then we just need to keep track of the tj variables and see when they are active or not. And these two types of Poisson processes are competing, one to activate as much as possible and one to deactivate as much as possible. So what we do is basically put everything together, and then we can have this dynamic equation here, and this is actually the exact model. There are no approximations so far. This model is, this equation is quite nice, but it's not practical. It's something that we cannot really solve numerically because here we have 2 to the power of n equations. Note that I'm saying 2 to the power of n because to keep track of this, we have to calculate all possible microstates. So we have a vector with n nodes that can be 0 and 1, similar to this table here. So if we want to solve the exact equation, we have to calculate all the probabilities. And this is why this equation cannot really be solved for large systems. So what we do, we try to do a first-order approximation. We basically assume that the states of the nodes are independent, something that we know it's not true, but something that we can calculate. And now the equation that I presented on the previous slides makes sense because we can use it to actually calculate things in our hypergraph. So with this, we have a first-order approximation of a mean field kind of equation that can describe the states of the nodes at any given time. Now, since we have defined our model, we also need to define our simulations. And our simulations have to be compatible with the definition of our model. What I mean by that is that I really need it to be a continuous time model. It's not a discrete time simulation. And this is quite important. I'm not going to get into the details of the implementation of this, but what I wanted to give is the basic information that we are going to simulate Poisson processes. We are going to get all the Poisson processes that I just defined, and I will simulate them. So I'm going to deal with the vectors of time. So I'm going to try to calculate when the next event will happen. In this way, I will keep the continuous time nature of the process, and I'll be able to see the evolution of our system. And finally, the last detail about this, the model, and more specifically about the Monte Carlo simulations, is that our model is finite. Everything that we do on the computer will be finite. So we have to deal with the finite size effects. And our system has one single absorbing state, which is the all zero state. This is the only state where there are no activity. And since this is a finite state Markov chain, we will always reach this zero state. This is, if we solve our equations, we are going to get zero all the time. But we are not really interested in that. What we are interested in are the metastates. So as the system grows, there will be some metastates that will be stable for some time, and then they will go to zero. So what we want to do is to capture on our simulations this state. To do that, what we do is to avoid the absorbing state. And we are going to use the so-called QS method, where every time we get to the absorbing state, what we do is that we go back to an active state that we previously visited. And finally, to characterize our system, we are going to use two different metrics. First, the average, which is how many, what's the fraction of the population that is active. And second, the susceptibility, which is basically the variance over the average. The average is natural. It's something that we actually want to understand. And the susceptibility will tell us the variations over this average. And for the physicists here, this is very natural because this tells us a lot about the nature of the phase transition. So in the critical point, if it's a second-order phase transition, then we will have a peak, and this peak will diverge as we increase the system size. So this kind of information tells us a little bit more about what is happening behind the order parameter. So, okay. Now we have our simulations, and we have our model. So to summarize the results that we got, we basically got one real network, which is this Blues Reviews hypergraph. It's people reviewing music on Amazon. So if two people review the same song, they are on the same hyperedge. I understand if you argue that, well, this is not the best hypergraph to model a social system. That's true. I give you that. I agree. But the truth is that we don't have so many real hypergraphs that have, real correlations, structural correlations. So our first trial was, okay, let's get the craziest hypergraph that we can find and see if we find something different. And the truth is that we found a very completely different behavior, especially if we compare to a graph. In a graph, what we would expect, the graph would be a simple SIS process. In a graph, what we would see is a second-order phase transition and one stable branch. In our case, what we see is multiple stable branches, as you can see here, there are 1, 2, 3, and the 0 should be stable as well. We found multiple transitions, so one here, one here, one here, one here. So even this red branch, you can see 2 transitions in a row. We found that the transitions are discontinuous, like here and here. And here we can perhaps argue that we have a continuous transition as well. And all of this, I want just to emphasize that all of this is not really expected. So here we have to understand a few things. First, what is causing this? So to try to understand this, we got this real system. We broke all the correlations by reshuffling all the hyperedges. And we checked, is this based on correlations? Are the real correlations that I was mentioning before generating this? And then we can see on this blue curve, yes, it's partially true because we have one single transition. It's true that the transition is still discontinuous, but a lot of the things that we found here are based on correlations. But not everything. We still have the discontinuities. So the higher order effects are still playing an important role here. Now, focusing a little bit more on the real system, the real hypergraph, we checked the susceptibility on all of those transitions because we want to understand the nature of these transitions. And what we noticed is that those transitions are one side, they diverge just from one side, and they are still discontinuous. So we cannot say this, but this suggests that we have hybrid phase transitions because, I'm saying that we cannot say it because it's a finite system, and without doing the proper finite size analysis, we cannot say the real nature of the transition. But this is a thing that we have to deal in networks all the time. Every network that we do is not just a hypergraph kind of special property. This is actually a problem of finite size analysis, not analysis, but the finite size systems. So going back, we found that we have many transitions that are diverge from one side only, suggesting hybrid phase transitions. Also, we want to understand why do we have, and what is happening for us to have multiple stable branches. To be honest with you, when I saw this graph for the first time, I thought that all my code was wrong, because it's not really possible, right? So what we did was, okay, let's try to look deeper. So we chose a few points here, and then we tried to look at the distribution of states. And from the distribution of states, what we realized that is happening is that we have bimodal distributions of states. So in a graph, what we would have is a bell-shaped distribution where the average defines the only branch. And with this model, we have bimodal distributions. And as we increase the spreading parameter, the two modes are going up and down. So, okay, this kind of explained a little bit. But it creates another problem. What kind of process generates a bimodal distribution of states? So what we did was to plot the evolution of the system over time. And what we realized there is that we have intermittency. So we have some regimes when we have high and low activity, as we can see here and here, for example. Or even here, it's more clear. So these branches, they might have besides the multiple stable branches, they can also present intermittency as well. And we can also find the simple branch that would be similar to the SIS in the graph, for example, in this green line here. Okay, so since we have bimodal distribution of states, it doesn't really make sense for us to look at the average itself, because the average is the only point that, is the point that we have the least probability. So we propose to look at the peaks of this distribution, the most likely points. And here comes the fun part. If we plot the peaks for the same range of values, of lambda values, we have something like this. But then, if we solve our first order approximation, we get this kind of plot here. So what our mean field approximation is doing is actually capturing the peaks of the distribution of states. And it might sound surprising at the first time, but then you realize that yes, that's exactly what should happen, because in the mean field, we do not account for stochasticity, and we do not account for the dynamical correlations as well. Yes. Yes, you should do the second. Yes, the problem is that. Yes. Yes, 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 exactly, exactly. No, of course. I mean, this is the first approximation that you do. And as I said at the beginning, the idea here is to just start. Uh, the first trial is the truncating on the first. Yes, exactly. Yes, 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 yes. No, no, no. What I can tell you is that we are working on higher order models as well. But the point is that, let me go back. For example, here, this equation, like from the practical point of view, not from the theoretical point of view, here we have an equations, but this term is also way more complicated to calculate than what we have in the graph. So in practice, if we go for higher, right, truncating on the pairwise or triples and so on, the number of equations already grow very fast, but these kind of terms also will grow very fast. So in practice, this might be problematic, let's say. But in theory, you're right. We have to go to higher order approximations as well. Did you answer a question? Yeah. Yes. Yes, 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 yes. Sorry, maybe I didn't. No, 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 but yes, yes, yes. Yes, yes, but the point is that this peaks breaking, like in what sense? Um, Maybe, but I honestly don't see why. Yes, yes, we can, we can. That would be nice. But the point is that, the mean fields, the way I'm seeing is that it's capturing the most likely values. The mean field is not seeing the bimodality because the bimodality is a consequence of stochasticity. It's you're here, but then eventually you go there due to some stochastic fluctuations, and the mean field doesn't see this stochastic fluctuation. Okay, but then I'm changing my mean field. Yes. No, okay, now I understand your point. Yeah, but then if I go to the exact equation, I do get that, and I'm showing this later. Okay, but we talk later, and then you tell me if I helped, uh, well, with the next slides, hopefully. So, okay, what I wanted to mention is that it's actually capturing a lot of our dynamics, but not really the dynamics of the average, but the dynamics that is on the peaks. So in this spirit of trying to understand what is actually generating this, we started to investigate, what is happening, what is the structural properties of our hypergraph that is creating this kind of new behavior. So the first thing that we did is to plot the adjacency matrix for this specific hypergraph, and then we realized that we have a strong community or group organization there. So in this case, what is actually happening is that our process is being localized in different structural parts of our hypergraph. So if we get the upper branch, what we have is that the whole hypergraph is active and the activity is spread in the whole system. If we get the branch in the middle, basically this community here is the one that is active. And finally, if we get the lower branch, we have that this community here is active. And notice that the IDs of the nodes are here, are the same of the IDs of the nodes here, and then I ordered it in a way that is easy to visualize. Okay, but this doesn't really explain the intermittency yet. The intermittency was present on this branch here, so we try to plot the evolution of our system, the activity of our system, as a function of time. And then what we realize is exactly what I was saying before, that we have, in this case here, the activities on this small group of nodes here that are very well connected, and they are able to sustain the activity for a long period of time. However, this is still connected with a lot of other nodes, and due to some stochastic fluctuation, what we do is that we spread this to the whole community. But then, due to another stochastic fluctuation, it goes down. So we have these stochastic fluctuations infecting or activating the whole community and staying in this small group. So this is what is happening in this intermittent behavior. And if we want to plot here, it would generate these bimodal distributions as well. OK, so as I said before, this hypergraph is not the best hypergraph, because it's not really, it's good for me to give examples and show that this kind of crazy behaviors, but to understand what's really going on, it's better for us to go back and to analyze some artificial systems. So what we did was, OK, hypothesis. It's our community structure that is generating this kind of behavior. So let's generate a community structure kind of hypergraph, and then we are going to add bridges between two different communities, and then we are going to see the behavior, and we are going to test if the community structure is actually generating this behavior or not. I must emphasize that we have two communities with different densities. So this is just to create one community that activates easier than the other one. And what we realize when we have just a few bridges, we have multiple stable branches. As we start creating new bridge hyperedges, this multi-stable kind of system changes to one stable solution, but with bimodal distribution of states. And then if we keep adding more bridges, then these B-stable regimes shrinks and move to the left, so a lower spreading rate, which is kind of expected, especially expected given the results that are presented in the previous slide. However, this is not the only kind of ingredient that's generating this multi-stable and intermittent behavior. So bridges is just one, but how wide those bridges are also play a similar role. So if we increase the size of the bridges, we see the same kind of behavior, the same kind of interplay between multiple stable branches and intermittent solutions. And finally, to answer our reviewer, we also tried to challenge ourselves and said, OK, if I can create as many branches as I have based on the number of communities, maybe I'm able to create as many branches as I want. I want to be able to create the diagram I want. So we created a 4-community kind of system, and we tried to see if we could control the number of stable branches. And the truth is that we can, but it's not so easy. And another phenomenon another thing that I wanted to mention is that the role of the critical thresholds. That as we reduce the critical threshold, it's easier for the activity to spread to the different communities. Then we lose the multiple stable states and have one single state, but we have the intermittency present in the others. This kind of interplay between multi-stability and intermittency, and when theta is smaller, it's easier to spread, and then it's easier to have intermittent behaviors. So we have basically three ingredients: the number of bridges, we have how big they are, and we have how easy it is to activate those bridges. So, okay, with this, we get a good understanding about the intermittency and the multi-stability. But I mentioned that we saw some one-sided divergences. And in these one-sided divergences, I said that one hypothesis would be that we have hybrid phase transitions. So how can we have at least some extra evidence about these kind of phenomena? So we went to the simplest thing that we could, and we proposed to analyze this hypergraph that we call a hyperblob. A hyperblob is basically a random regular graph with a complete hyperedge that gets everyone inside. The good part about this one is that it's a very simple system, and then we can simplify our system, can simplify our equations actually, and then we can calculate the distribution of states, hopefully exactly. And in this case, since the states for us will be the number of active nodes, we are going to have a Markov chain that looks like this one here. And then what I would like to point is that I'm starting from 1 because I'm already deleting the absorbing state. I want to calculate the metastable states. With this, we can just obtain the transition rates. This is very simple, and this is basically drawn here on this graph. And then we can solve this equation because it's actually very simple. And unfortunately, we don't have an analytical expression for this. But what we have is an algorithm solution that can be solved in order of n, in order in complexity. The computational complexity of the solution will be n, which is way smaller than the 2 to the power of n that I mentioned for the other system. And all of this is due to the structural symmetries of my system. So just to compare our mean field, the one that I mentioned before, with the simulations, here I'm plotting in the continuous lines in blue, red, and green. I have the solution of these exact equations here. And in gray, I have the Monte Carlo simulations. And you can see that they are matching quite well. Just a funny comment about this. When we published our first paper, we had the green ones. And when I saw this small peak here the first time, I thought, this is probably some artifact of simulation. It's just that I probably didn't simulate long enough. When we come up with the exact model, then we were able to find that this was not an artifact. It was actually there. Of course, let's not forget that there is a small displacement here between simulations and the exact model. And my claim here is that this is probably because the simulations themselves are quenched. They are on one single system, while these equations here are based on an annealed kind of system because we are using the symmetries of the system. But we are still capturing everything that we were expecting. And next, since we have this mathematical model here, we can do some kind of numerical approach, having the finite size analysis. We have the steady state solution for our quasi-stationary model, so we can calculate any moment of the distribution, and we can actually check if our transition is actually a hybrid or not. And what we did was, with all those plots, we showed that the discontinuity appears on the infinite size, and that the scaling parameters are below 1, which are the necessary conditions for the hybrid phase transition. We cannot say that what we see in general systems are hybrid phase transitions, because they are very different from this very simple model. But we have one extra evidence that, maybe those divergences that we saw at the beginning, maybe they are due to some hybrid kind of transitions. Okay, so let's try to conclude a little bit. So how will a collection of groups behave? This was one of my first questions. So the question is, the answer would be somewhere like crazy. It's very different from what we expect from graphs. So far we found multi-stability, intermittency, we found multiple transitions, and I'm pretty sure that there are other behaviors that we just didn't find. How will the intersection between these groups change the global dynamics? So the thing here is that the intersections are creating this multiple stable branches and these intermittent and bimodal distributions. And finally, can smaller groups have a higher critical mass? Smaller groups have a higher critical mass than the whole population. So the idea is that in the literature, in social sciences and political sciences, we had this 25% or 20 and 40% range. But this is for one group. So the intersections between those groups can generate and can trigger a cascade on the global population. And then in global terms, this jump can happen with a way lower critical mass, basically. So committed minorities can trigger global changes. This is the kind of interpretation with all the small details, the details that we have to put, because this is just a mathematical model. Okay, this basically concludes the idea of the social contagion model. Okay, the social contagion model in the context of social and not disease. But this is a way bigger problem. I mean, not problem, way bigger system. The idea, the mathematics behind is much more general than just the social contagion, which is basically for norms, ideas, not really for disease. But then we can also have problems like how information in hierarchy systems behave. We have social groups. That is basically what I was talking and trying to model. And the way I was trying to model, it's important to say that is my biased personal way. There are many other models, many other people that are trying to model similar phenomena using different ideas. And so what can we say? How can we use the ideas that I just presented in all of those other systems? So the idea here is that we can use this knowledge in kind of a general formalism, where we use basically what I presented here is just one specific coupling function. But we can slightly change the equation I showed at the beginning into a more general framework. And in the literature, what we have is that by using this kind of equation, we can simplify our model to the classical pairwise graph case. It fits the same way. There are specific models for diseases like this SIS on hypergraphs, where they use this kind of function that is increasing, but then you just stop at an arbitrary value C. We have the simplicial contagion model that the interaction basically accounts for. The interaction is actually created when you have a hyperedge, and then you consider that the extra force of infection will appear only if you have all the nodes active but one. And we can also have this kind of power law infection kernel where you create this parameter here that you can use as a social reinforcement or some kind of reducing the interaction as well. And another idea that I would like to try to share with you is that higher order can have many different flavors. For the one-to-one, the pairwise case, it's very simple. It's just one interaction. But for the higher order, we can have one too many. That would be like what I'm doing right now. I am passing the information to everybody at the same time. But we can have many to one, that all of you, for some reason, don't like me and try to come at me at the same time. And the many to many, that would be actually the ideal one that we kind of discuss all of these ideas together. And we would like to kind of propose that this can be used even to different systems, not only the spreading models that I'm presenting here. So the actual conclusion is that by using these general ideas, we want to try to really understand what are the general and particular aspects of these models. Since we have this equation here modeling all of these types of interactions and even more, any arbitrary function here. So what is actually general and what is actually particular of these models? And this is important because I publish a paper on my model, and then you, like a different model for some reason, you can use my results, and you know how far my conclusions apply to your system as well. The same applies for the particular results. This is one of the reasons. And another reason is actually to understand how strong is the hypergraph structure. How strong are the dynamical and combinatorial properties of those objects, creating some constraints in the dynamical system and the output of these dynamical systems. And just to conclude, this opens a little bit of opportunities for data-oriented kind of studies, because we have a lot of data from online social systems. We have a lot of data with COVID, for example, that we can try to use and think about, one-to-many or many-to-one settings that we have. I don't know, in one household, we can create a hyperedge instead of a small click. We can also think about proposing new controlled experiments in the spirit of the first study that I showed at the beginning with the Professor Kelly. And of course, we have opportunities for new applications. So understanding when we are going to have social tipping points. So I don't know, a norm is going to change. Some political idea might change. And this can be drastic. But if we can somehow understand when it's happening, we can be prepared. This is modeling as well. And to give one engineering kind of application, wireless communication can also profit from this kind of theory as well. At least that's what I hope. And that's it. Thank you.
Any questions?
Hi, Guilherme. Thank you very much for the very nice presentation. Well, when you define the model and you talk about how do you do the simulations, you define a Bernoulli variable, right, for
Yes.
each node.
Yes.
And I have two questions, actually. How do you define the initial conditions, and does it matter for the final results of the simulations? Thank you.
Yeah, it does. It does matter. Yeah. This is actually what is leading you to one or the other branch. If you start, for example, this is a bit slow. Like, if you start here, you are going to have one solution. If you start here, you're going to have another solution. And if you start with everyone, you can have another one. It depends. The initial condition is actually playing this an important role on which branch you are going to enter. Did I answer your question?
Other questions?
Hey, thank you, Guilherme, for your nice presentation. I have a broader question. So I've been a bit far from theoretical side of things for a while now. So since you started working with hypergraphs to now, I remember when you started, there was a lot of hype on that, like novelty, and also challenges. And how do you feel that the area is now about the hype and the challenges?
Well, I don't know. This is very difficult.
No worries, no worries.
I think that it's kind of complicated because there are a lot of people trying to work with that. And there is one thing that we didn't mention, that I didn't mention, like at the end. I think there is kind of a misunderstanding sometimes what is actually higher order. Because I can create a hyperedge and define a function here that is just a set of pairwise interactions. So my structure is higher order, but my dynamics is not. So it's actually that the dynamics is projecting into a graph. Then I don't know, is this higher order? I would argue that not really, because the actual object is a graph. So I think there is a lot that we have to understand in these lines. And I think that, I don't know, as a community, we have to make the mistakes and move there, I guess. Myself included, I'm making them.
Okay, thank you.
There is one.
Congratulations for your presentation. We are in the extremely opposite in terms of disciplinary fields and comparison of the problem, social problems, né? Because you are from the math and statistical, etc., complex system, and I'm from sociology in terms of qualitative methods. Wherever I'm doing a great effort to interact with the people of complex system, with the group of Celso Grebogi in the University of Berlin, particularly with Murilo da Silva Batista. We have 3 different papers. Some of them are in the references in my banner there. And the problem that I would put for you is about which social theory you are based on to build your problematization, your issues, your problem of research. It's a very important question for me, if you don't mind, because the sociological theory or the social theory in terms of humanities and abroad, you choose one type of data set, the confiability that the data set have to create in this point one problem that is useful for to base public policies, etc. And I don't see specifically the social theory you are basing from, because you have 2 or 3 different paths, paths for understand this kind of social or social environmental problem that you exemplify there. Thank you very much to clarify it.
Okay, thank you. Thank you for your question. I don't know if I can answer adequately. The work itself is basically, mathematical. We didn't make any kind of extrapolation to real-world problems, and this, we were very clear about the limitations in the sense of, okay, this is a mathematical model. We are based our ideas on the assumption that groups behave as this kind of have-side functions. So I think that in sociology, this is, okay, let's assume that the critical mass model is correct. So from this, let's extend to the hypergraph, to the bigger system. I understand your point, but I don't know. To my understanding, this will be a more important question if I move to the applications, right? Because what I'm basing my argument is that so far is mathematical, and I'm creating the mathematical ideas that can be further explored by the sociologists. I'm not trying to make any sociological claim. Although I have some ideas, like personal ideas, I hope I didn't put them in the work. I try to be as external as possible in social terms. I don't know if this is enough for you, but maybe we can talk later if you're available.
It's a very difficult dialogue, né? To build together the issues, the mathematical point of view, the sociological point of view.
Yes.
Né? It's a long-term effort that you have to do. We are from São Carlos too, Federal University of São Carlos, né?
Okay.
And we are building a dialogue with computational science too, né?
Okay.
Maybe we have to build together, né?
Yes.
This
I mean,
dialogue.
if you are available, I would like to have a deeper discussion about this. I would love to.
Thank you very much.
Thank you.
Yeah, one last question we have.
So Guilherme, thank you for the talk. Just when you say to compare models,
Okay.
yeah, just a quick remark. For example, you're from São Carlos, right? So they
Yes.
have a huge singularity theory group there.
Mm-hmm.
Because you see many of the phenomena like multiple branching can happen in network as well.
Yeah.
So I think these people, they, for example, in your equations, they are kind of Kolmogorov type population model, right? I think for this type of equation, the kind of dynamics you see depends on how many parameters you can tune.
Okay.
And this goes back to Arnold, and he goes classifying this kind of functions. I think, I don't know this very well, but in São Carlos, they know this quite a lot.
No, good. Thanks for
It's
the
basically
remark.
classification problem of functions.
Okay, classification problem functions.
Yeah, and so you have functions of many variables. So if the functions are pairwise, you call network. If three
Yes.
variables, you call hypergraphs. But I think if you talk to them, they will say how many parameters can you tune? And depending on this, they will give you the normal form of the function. And from this, you get your dynamics. Just to say, call your attention to this field.
No,
Yeah.
perfect. Thank you. I really appreciate that. Thank you.
Well, thanks again, Guilherme.
Thank you.